Alright, so let's take a look at problem number 3. Now, if many Algebra 2 students, when they first look at problem number 3, think they're stuck and these problems cannot be simplified. The reason why they think that is because take a look at the radicands. Remember that vocab word, the number underneath the square root? We have a 12, we have a 75, and we have a 3. So then what we might be thinking about is it might be a situation like these guys right here, where if we don't have, say, the same number underneath, that we can't simplify them. Au contraire, mon frères, take a look at this problem and see how sometimes you might be able to there might be ways of untying these knots. So, the trick to untying these knots is understanding what the key difference is with this problem versus the other ones in, say, problem number 1, is that when you look at, say, the square root of 12 and the square root of 75, they can actually be simplified using other numbers that are perfect squares. Now look at the one number that actually cannot be simplified with perfect squares, and that's the square root of 3. I will say this. In many, 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 wink, 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 nudge, 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 in many, many situations, if you can find the one that's already simplified and you cannot simplify it, watch this little cheat code when it comes to the other two. If I'm looking at, say, the square root of 3, which I'm looking at right now, and I suppose, I don't know, what would happen if I were to say take that 75 and divide it by the square root of, I'm sorry, not divide it by the square root, but just divide it by 3. Wouldn't it be true that we would get a number, say, I don't know, 25 times 3, and oh look, what a coinkydink that 25 is a perfect square. I wonder if that would still work here with the square root of 12. If we take that 12 and divide it by that same old 3 that's right there, sure, we'd have a 3, and look at the other factor. Oh look, a perfect square of 4. I will tell you, this will get you out of many a jam if you find that number that is already simplified and just simply use division, and that other factor will be the perfect squares that we need. In fact, do you see what I have right here in red and right here in red? That's this step right here. Okay? They took that square root of 12, broke it down into the square root of 4, which is a perfect square, times 3, plus the square root of 25 times 3, and then minus 1 square root of 3. Now these next two steps, they break that 4 down into the square root of 2 squared, which allows them to break that down into 2. But like I've said in many other lessons, ladies and gentlemen, feel free to skip this step, and then also feel free to skip this step right here. Okay, so it's perfectly okay for you to go from here right down to here. And does it make sense where those numbers are coming from? Okay, let me grab the highlighter here just to make sure that we're all on the same page here. The square root of 4, that's your 2. The square root of 25, there's your 5. Okay, and then let's take a look at what's left over. We have a square root of 3. We have another square root of 3, and then we have that subtraction of that square root of 3 that's still there. So ultimately, what do we have here? Don't we have 2 square roots of 3? Plus 5 square roots of 3, which gets us a total of 7 square roots of 3. And then aren't we subtracting just 1 square root of 3 to put us at a total of 6 square roots of 3? Does that make sense? Okay? So don't be so quick to say, oh, it's already simplified. Make sure that you can do these tricks here first. If you flip back and flip back again, take a look. Did we even have that as an alternative on, say, look at B right here, square root of 7, square root of 5. Nope, couldn't have done it. See right here, those are cube roots and square roots, so we wouldn't have been able to do it anyway. Okay? So, now it's your turn. Let's take a look at this one here. Now, I will get the ball rolling here. I will help one more time. Take a look at this right here. Notice they are cube roots. So, we do not want the list of perfect squares. We want, once again, that list of perfect cubes. Okay? Might not be a bad idea to have some of those memorized. Now, remember that wink, wink, nudge, nudge, really, really awesome little cheat code that you might have right here? That doesn't necessarily work right here, because if you look at all three of these numbers, 250, 54, and 16, actually, I don't think any, nope. So one of these numbers, you're actually going to have to break down each one of these. Okay? So, give that one a try. See if you can work your way out of this mess and try and get what we're trying to get here is the same cubed root 3 times in a row, so that way we can combine like terms. Okay, pause, try it. All right, had a chance to try it? Great. All right, so let's see here. Well, I'm going to pick on that 16. You know what I could do with that 16? That 16 could be broken into 8 times 2, right? That's good. How about 54? 54, that can be 27 times 2, right? Right. And then how about the 250? I think the 250 can be 125 times 2. These 2's, good sign. Very good sign. So I could rewrite this guy as a cube root of 125 times 2 plus a cube root. I haven't said this very much here very often, but when it comes to writing other roots besides cube roots, here's my little analogy. Don't let that 3 float too far out here, because now it looks like you're doing 3 times a square root. Here's a really, really goofy analogy. Pretend that the square root symbol is a kangaroo pouch. Make sure you take that root, that cube root, put it right there in that kangaroo pouch. Okay? And then all is well. I know it sounds silly, but ladies and gentlemen, that will really help a lot of us mathematicians making sure that we're checking, and a lot of math teachers check your work to make sure that you're actually showing a cube root there. So put it right there in that kangaroo pouch. So where was I? Oh yeah, 27 times 2. Okay? The 2's are nice. And then the minus sign, and then cube root, kangaroo pouch. And then we have 8 times 2, right? So here's what we're going to do. We are going to take the cube root of 125 and the cube root of 27 and the cube root of 8. And let's get all of those. If you need a calculator to help you out, so be it. Use the calculator to help you out. But I'm pretty sure 5 times 5 times 5 is 125. So then that would give me 5. Now careful, this is what I'm talking about, the kangaroo pouch stuff. Okay, put that cube root in that kangaroo pouch. Make that font size even a little bit lower. It's like literally font. See how big that 5 I wrote? Make that 3 even tinier and put in that kangaroo pouch. And then cube root of 2 plus cube root of 27. I think that's a 3. Make a big 3 and then make a little itty bitty tiny 3. And then kangaroo pouch and then the 2 and then minus a cube root of 8, which would be big 2, little bitty 3. And then cube root of 2. Okay, so now I have like terms. Or like radicals here, I have 5 of those cube roots of 2's. Let's add 3 more of them to give us a total of 8 of them. And then after those 8, oh, we lost 2 of them. So now how many altogether do we have? I think we would have 6. Big 6. Cube root of 2. It's a big hero 6. Alright, I'm done talking about this video. Let's move on to the next one before the jokes get even more lame.